Suppose I gave you 100 snow profiles, half of which were from slopes that had been skier triggered, and half from slopes that had been tested by skiers but not triggered. If asked to sort the profiles into two stacks, skier triggered or not, how many would you put in the right stack? This video is about an objective method, a checklist, that puts about 2/3 of the profiles in the right stacks. The method also offers some ideas on how to interpret snow profiles. So here is a manual snow profile of the top 75 centimeters of the snowpack. These lines indicate the layer boundaries. Here is a bar graph of the hardness of the layers. These symbols indicate the grain types. Here are the grain sizes in millimeters. To the right are the columns for the yellow flags relating to the layer and interface properties. Here are the yellow flags for layer properties. If the primary grain type is persistent, that is surface ore, facets, or depth ore, the layer is assigned a yellow flag. If the average grain size is greater than 1 millimeter, the layer gets a yellow flag. If the hand hardness is less than 1 finger, that is softer than 1 finger, the layer gets a yellow flag. For this method, it is helpful to assign numbers to levels of hand hardness. 1 for fist, 2 for 4 fingers, 3 for 1 finger, 4 for pencil, and 5 for knife. Further, if the observer has assigned intermediate values, such as 4 finger plus or 1 finger minus, these are given values of 2.3 and 2.7. For more on hand hardness or other layer properties, refer to Snowpack Observation Guidelines or the 2005 paper with Schweizer. Here are the yellow flags for the properties of each interface or boundary between layers. If the difference in grain size between adjacent layers is greater than 0.5 millimeter, interface is assigned a yellow flag. If the difference in hardness between adjacent layers is greater than 1, the interface gets a yellow flag. If the depth of the interface is between 20 and 85 centimeters below the snow surface, the interface gets a yellow flag. Using numbers for hand hardness, a hardness difference from 1 finger plus to 4 finger has a value of 3.3 minus 2, which equals 1.3. Okay, now let's apply the yellow flags to the profile we looked at earlier. These layers have an average grain size greater than 1 millimeter. For the melt-freeze crust, we assume an average grain size of 1 millimeter, which is not quite big enough for a yellow flag. These layers have a hand hardness less than 1 finger. Only this layer has a primary grain type that is persistent, in this case, rounded facets. These three interfaces have a grain size difference greater than 0.5 millimeters. These interfaces have a hardness difference greater than 1. These interfaces are between 20 and 85 centimeters below the snow surface. Now let's add up the flags for each interface and adjacent layer. If both adjacent layers have a flag for a specific property, we only add one flag for that property. The first interface is about 16 centimeters below the snow surface, has no yellow flags for interface properties, and 2 yellow flags for layer properties, 1 for grain size and 1 for hand hardness. See the interfaces above and below the rounded facets, about 65 centimeters below the snow surface, have 5 and 6 flags. 5 or more flags turns out to be critical, shown in the next slide. This profile was observed on a slope where a skier triggered a whoomph, which would have released an avalanche on a slope that was steep enough. 67 to 75% of the profiles from skier-tested slopes with 1 or more interfaces with 5 or 6 yellow flags were skier-triggered. 60 to 65% of the profiles on skier-tested slopes with an index of 4 or less for any interface were not skier-triggered. Of course, being right about the triggerability of the snowpack 2/3 of the time is not nearly good enough. Snow profiles are just one piece of information that can be used to assess instability. Yellow flags, or lemons, which were previously developed by McCammon and Schweizer, are also called structural instability indices. They supplement other indicators of instability, such as snowpack tests. Although this video does not provide a physical interpretation of yellow flags, the papers mentioned in this video do so. These indices can also be used for teaching snow profile interpretation. Although it has not been proven, this slide shows the hypothetical variation in compression taps, fracture character, or yellow flags on a slope. We see the number of taps in compression tests varying from 12 to 24. Fracture character is consistently sudden planar or shear quality 1, and the yellow flags, YF, only varies between 5 and 6. Here are some limitations of the yellow flags method. The index is only accurate about 60 to 75% of the time and only calibrated for skier triggering, although triggering by snowmobiling may be similar. In other words, the method did not identify the same critical layer as stability tests in about 30 to 40% of profiles. Also, it over or underestimated the stability of the adjacent slope in about 30 to 40% of the time as well. These results are based on dry snow profiles from skier tested slopes in the Columbia Mountains. Profiles from other snow climates have been analyzed. See the 2002 ISSW paper by McCammon and Schweizer and the 2004 paper by Schweizer and colleagues. The method requires fairly detailed profiles. Doing a snow profile on each avalanche slope to be skied or snowmobiled is impractical. Structural instability indices, such as the count of yellow flags, should be interpreted along with the avalanche observations, recent weather, the results of instability tests, observations of fracture character, and of course, snowpack distribution over terrain. In summary, the yellow flags methods helps us identify most critical weak layers and which properties are important. It is a simple way of summarizing individual snow profiles. It can be used for teaching snow profile interpretation and is based on evidence. As a training tool for snow profile interpretation, the yellow flags method teaches us to focus on soft, coarse-grained layers, especially when just above or below harder, fine-grained layers between 20 and 85 centimeters below the snow surface. I am grateful to the organizations shown here that supported ASARC during the years the yellow flags method was developed. Thanks to my co-author, Jörg Schweitzer, and thank you for watching.